Hey everyone, welcome to part 2 of the Yamaha SPX90 Series 2 repair. So, in part 1, we got this unit working. Power supply was the culprit. Leaky caps, replaced them all with Panasonic 105 degree C-rated caps, really high quality caps in there. Cleaned up the board, got rid of the electrolyte that had leaked on the board that was causing problems. Tested it out. 5-volt rail was a little low, so we adjusted that with a small pot and power supply there. Verified everything was good. Unit does power up. It was passing audio. Levels on it were still low. One of the reasons for that was because the capacitors on the main board, specifically in the analog digital analog section, were also bad. So that was the next step that we needed to tackle, and that's one of the first things we'll be discussing in this video. Secondly, after we look at that, we're going to look at the architecture of this. This will kind of tie into the teardown. In terms of how this works, what hardware they were using back in the late 80s when this thing was built. It's pretty interesting the way that these older DSP units, were designed and engineered. I mean, it was really cutting edge stuff at the time that they were doing. Yamaha was one of the leaders, along with Lexicon. A couple other guys out there too. Alesis was doing a really good job with their DSP. Yamaha specifically, though, I've always liked the Yamahas. They had really good sound. And Yamaha has always had really good DSP, and this was kind of the early, origination of that DSP that still carries on this day. So in part 1, I talked about the caps we were using. In terms of the power supply caps, I'm using 105C rated Panasonic, various different series in there, but really good low ESR caps. For the audio side of things, I'm using ELNA caps. In this case, the RFS series. So these are really high quality caps designed for audio purposes. They're a very good replacement to the Nishikans that are currently in here right now, which at this point are 30-some years old and due to the heat have just failed. So the ELNAs are really good caps. Now, one thing I didn't notice when I first looked at this is that some of the caps in here, specifically in the audio pathways, are actually non-polarized, including these two back here. There's two more up there and a handful over here as well. So I don't have any non-polarized ELNAs in stock or with me at the time, but I do have the Nishikon Muse caps, which are also a really, really good high-quality electrolytic capacitor. And these are non-polarized caps, or bipolarized, however you want to call them. So I will be using these for these non-polarized caps that are remaining instead of the ELNAs. Again, still a really good cap, really high quality, designed for audio purposes. And those will be replacing the remaining caps I have on this board here. So if you have one of these Yamaha SPX90 or 90 Series 2s, which the two models are virtually identical, you're going to have to replace the caps in them by this point. If you haven't already replaced them already, that is, or somebody else hasn't done it by now. They just don't last that long of a time. Granted, if it's new in box, been sitting for 30-some years, barely or never used, then you might be okay. These caps still have a shelf life, though. After sitting around for that long, they do start to deteriorate over time. Especially, some of the older ones. The newer ones are made to a lot higher standard now, especially the lot higher grade caps you can get. So I've already gone through in terms of saving time and replaced a lot of the caps on this board. For caps on the power rails, including around the 7815, 7915 regulators for the actual analog digital converters, I use the same Panasonic 105C rated caps that I did in the power supply. For all the caps along the audio circuits, specifically that we're passing or near passing audio, I use the ELNAs, RFS series caps in there. The ones remaining that I have are the the bipolar caps that I'll be using the ELNAs for, which are these two right here. And then I've got two more snuck over here. I've got two more up front right there, and two right there. So 8 caps in total that are bipolar on this board remaining. There was also a couple over here on the power rails that I snuck in as well. So if you're going to do this, make sure you do them all. There's no reason not to at this point. The last thing on this board that we're going to do on this repair is replace the battery, which sits right over here. I already cut this out because somebody in the past had replaced it and had just soldered it in. If I have it laying around anywhere over, I don't know what I did with it, but it was just a standard 2032 cell that they actually soldered wires to and then put tape around it so it didn't short out anything. But that's not the way to do it, so I bought proper batteries that I'll replace there. Ideally, I like to put a holder on here, so I'll see if I have a holder that actually fits this footprint. If I do, I'll stick a holder in, that way it'll be replaceable in the future. If not, I'll replace it with the same style battery that was in there, soldered in. Manufacturer says they only have a 5-year shelf life, but these things typically last 10, 15 plus years without issue, so it's not a big deal. Alright, quick look to see how bad these Nishikon caps actually are that came out of here. They're 100 microfarad, 16 volt, and the audio passes directly through these on the output stage, left and right channel on this unit. So just curious to see where they're actually at capacitance wise, because these ones are pretty bulging. They're not very happy. So we're only looking at about 50 microfarad on this, even though it's rated 100. Compare that to one of the brand new Nishikon Muses. And 94. So big difference. Roughly half the capacitance on that one. Again, this doesn't measure ESR, but I'm sure it's probably really high resistance as well. Okay, so the cap replacement is complete. Every cap on this entire unit has been replaced at this point. You can see the green caps are the Nishikon Muse, and then the brown ones are the ELNA RFS series, and then everything left in black is the power supply related caps that I put the Panasonics in there. So I mentioned this in part 1, I haven't mentioned it yet, but all the Panasonics I use are 105C rated. The Muse and the ELNAs that I put in this unit are only 85C rated. Typically I like to keep everything 105C, but I didn't have any 105C ELNAs or Nishikon Muse with me at the moment. So the 85s in here though will be fine, because they are situated pretty far away from anything that would get warm, including the power supply, and then most of the TTL logic over here. I mean, granted, the ambient temperature within this rack unit will still get pretty warm, but not hot enough to really be a concern to significantly shorten the life of all of these caps over in this area here. So these regulators make it fairly warm. I'm not 100% sure. After leaving it on a little bit, I'll feel them and see. In that case, I've still got the 105C rated Panasonics in close proximity to it to make sure that they don't get cooked from those regulators. But the last thing I need to do on this unit is replace the battery. So like I mentioned, I wanted to see if I could get a socket in there. I've got a couple different types. I've got the standard low profile sockets there. I checked already and it doesn't quite line up with the pins. I've also got a vertical socket, which I really like. That will actually still clear within the case closing if I were to put this in here. But again, the pins are just a little bit off. I'll have to bend them on there, bend them out to make it work, which I just don't really like to do. For this too, in the past I made small daughter boards just to make sure that it lines up correctly and sits properly. It doesn't look like it's just some hack that was stuffed in there to make it work. So because I don't have the right connector that'll fit that footprint, I'm just going to go with the standard 2032 solder in tab type battery, which basically is the OEM replacement, which will be fine. Like I said, you'll get 15 years out of one of these guys in this unit, so I will replace that next. Okay, new 3-volt battery is installed, so we'll power it up. I'm going to factory reset it as well during the power up, just because you don't know what state that battery backed up RAM is in. So to do that, you hold the balance and foot trigger switches while you power it on. And you can see it powers up. Hear the relays click, and we are good. We no longer have a low battery message anymore on the display either. So power it off one more time. Power it back up just to be sure. Everything looks good. So a few more things I need to do on this. Backlight display for the LCD is a little bit dim. You can actually replace the backlight on these. It's just a little EL strip on the back there. So it's not terrible. On the right angle it still looks pretty good, has good enough contrast, so I'll probably leave that for now. Alternatively, you could replace the display. It's just a standard HD 44780 type 2-line LCD. 2 by looks like 16 character display. So same that's in a lot of gear of this era. You can get them on eBay from China for $5. They're so insignificantly cheap. The problem is on this one, the pinout's actually on the side. A lot of the ones you find now actually have this is a two rows of I think 8 pins or 10 pins or something like that. Typically you find a single row of 16 or 20 pins, however many is on there. And because of that, it's not a direct drop-in replacement in terms of pulling this connector off and soldering it back on, so it requires some work. Because of that, and because it's still good enough, and you can actually just replace that little EL strip backlight there, which is also only a couple dollars. I'll probably go that route for this unit. Two, I'm going to take this front bezel off. I want to clean it up a little bit. I need to bend this dent out. I also need to see if I can find a potentiometer that size that will fit on there. The Yamaha one that came with it is a tiny little, I don't know what you want to call it, but it's got kind of a fin that comes out that you can actually grab and turn. I'm not going to have anything like that, so I'll see what I can have that will work. Ideally, maybe if I come across a parts unit of this or some other Yamaha gear, I can replace it with the correct one. I have the power switch. I took it off when I took it out, so I'll reinstall that when I put the front faceplate back on too. But so I will pull the front off and clean it up and reassemble, and then we can actually test it with some new audio. Okay, all back together. It looks much better than it did previously. I came across these small knobs that I have, which aren't exactly, it's not factory to what the Yamaha initially came with, or any Yamaha FX processor for that matter. This shares the same pots, the volume control knobs is like the Rev 5 and Rev 7, but it fits and it'll work for now. So I'll be happy with that for the moment. At least it'll allow me to test it a little bit easier. So, alright, next step is to power it back on, hook the audio cables up, and actually give this a test and see how it sounds. Alright, so I'll power it up, and I got it wired up here on my bench. On the, let's see, preset memory 1, which is Hall, reverb level 100, I'm assuming that's the mix. Much like before, I'm testing on my bench with my XP50, just for now, for testing purposes. Also, like I mentioned before, when I initially powered this on, after fixing the power supply, I'm just running it through my bench speakers here. They're little 3-inch, garbage speakers, PC speakers, basically on my bench. It's not going to sound great, so no judge of audio quality with this test. It's just more of making sure that I've got audio passing through, that there is reverb, that there is not any noises, any hums, any audio distortion, things like this that could indicate other problems with this unit that we need to look at. So, moving forward, we do have reverb, which is really nice. We'll bypass. So, it is definitely working. Let me actually turn the reverb off on the XP50 just to make sure that we're getting a completely dry signal here. Okay, so now reverb is off on the XP50. Hit bypass. So I think we're good. A better test will be to get this actually in my mini studio with the rest of my gear, get proper signaling through it with proper loudspeakers, or headphones for that matter, and actually give this a really good audio test with that. But I think we're going to be good at this point. The last thing I want to do is just kind of go through and look at the architecture of this. I've got the schematic here, so we'll start with that, and then we'll come back to the actual board here and talk a little bit about how the A to D and D to A conversion works. So now we will take a look at the digital and analog sections of the SPX90 Series 2. We'll walk through from the analog side first. So, single mono input goes through initial op-amp here. You got your input switching as well through some relays, and then the signal actually passes down this way through the filtering. And then this section here is where your actual analog-digital conversion is taking place. So, to better understand this, I think it may be easier just to look at the schematic. So here we are with a massive schematic for the SPX90 and SPX90 Series 2. They both share the same architecture and are virtually identical, minus a couple very little minor things, but they're insignificant in terms of understanding how either of these effects processors work. So this side of the schematic is the analog side, including the analog-digital conversion along with the DA converters as well. So it's a little bit more interesting, I think, in terms of how it works. So we'll kind of discuss the flow of signal basically through this unit from the analog side first, then we'll flip it over and look at the digital side and kind of see what they're using for the actual DSP. So following the signal in, here's your input. It's a single mono input. That was typical of most processors of this era. Some of the higher end stuff had stereo inputs at the time. For the most part it was mono. So first thing you do is you go through an op-amp, which is basically just a input level buffer, a little amplifier there, and then it feeds directly through that input volume pot on the front. This pot is the one I stuck the knob on there, so audio does pass directly through this. So if this gets dirty, when you adjust it, you'll hear scratchiness. And also, if it's kind of just in a dirty state there too, you could hear, you know, just kind of some noise from it as well. And this would be the culprit. So cleaning these usually fixes it. If it's beyond that and it's worn, you will have to replace it. Following through that input volume pot, you go through another op amp here, which is just another gain stage, and then you pass your first low pass filter. So in any type of analog digital conversion circuitry, you know, you're going to have a finite upper frequency limit that you're going to be able to convert to based on Nyquist, based on, you know, other specifications of design. So you want to cut all that additional high frequency components out of the signal early on. And that's what this initial low-pass filter is doing. This is actually a 4-pole filter, pretty expensive. So a lot of Lexicon units at the time, I know the PCM90 only had a 3-pole filter. So Yamaha is using a little bit better filter on their input stage here. You pass through a couple more gain stages, including your emphasis stage, or your pre-emphasis stage is typically called. So in any A to D conversion, DA conversion type circuitry, you lose a lot of the high frequency signal just due to the conversion process. So with the pre-emphasis circuitry, you're actually boosting the high frequency range of the audio going into the analog digital converter. So that's what that gain stage is doing right there. It's your pre-emphasis. So following the pre-emphasis, you actually come into what your analog to digital conversion circuitry is. So you don't have a dedicated analog to digital converter, you know, on this unit. Typically, when these were made in the time in the 80s, the chips that did analog to digital conversion either didn't exist or they were extremely expensive. So what people used instead was basically circuitry to do a successive approximation type analog digital conversion. So your successive approximation converter consists of pretty much all the components right here. You have a PCM53, which is actually a digital analog converter. Even though they have it labeled here as an analog digital converter, in terms of that circuitry, it's actually not. It's the same chip they're using for the output there. They're just using it to feed half of the comparator for the actual successive approximation conversion. Besides that, you have your 2 registers, which hold the current states of the data coming back into this digital analog converter that feeds the actual op amp. And then you've got 2 parallel to serial converters here, which are taking the data that's being fed into here and placing it back, you know, on that serial bus to the master DSP. So this is what's getting the analog data, you know, converted to digital back basically into the unit to be processed. So all of this here makes up that conversion circuitry. So now that you have your digital data going off the DSP, it does all its processing. It's got to get back, you know, converted to analog, and that's where your digital analog converter is coming in place here. So IC115 is another Burr Brown PCM53. This converter is taking the, you know, serial data off the bus. 2 registers here are converting that serial data to the parallel, feeding it onto this converter, and then generating your analog output, your analog waveform. So, or analog voltage, I should say. 2 neat things about this. This is a stereo output unit, but there's only 1 converter. It's because they're actually slicing the left and right channels back and forth. You can see the analog switches here that are actually doing that. So every other piece of data is to the left and right channel, and it's happening fast enough that, you know, it's quicker than you can hear. This is typically what most manufacturers did at the time. These chips are really expensive, so if they could get away with just using 1 instead of 2, they did, and pretty much everybody did this. So now that you have your analog waveforms coming off of this and you actually chop it between the left and right channels, you have a couple things going on here. You have a buffer amp, which is actually just an op amp here feeding your low pass filters again. Again, analog digital conversion is noisy, and DSP could be noisy. You can actually generate a lot of high frequency noise in there, so you're filtering that out here with more of these 4-pole filters like you saw in the input. Then you have your de-emphasis circuitry. That's to remove your pre-emphasis, which you added before, you know, on your analog digital conversion. So this is actually ramping that high frequency, you know, boost back down to near what the original waveform looked like. Through that, you've got a couple more gain stages there, and then finally your buffer amp on the output, which goes to your left and right channels, you know, out. All right, now we're going to look at the digital side of the schematic for the SPX90 and SPX90 Series 2. This is basically the master CPU that controls all the function of the unit. So it handles the DSP algorithm switching, it handles the interfaces to the RAM and ROM, both for the operating system that runs it and the presets, which also loads the algorithms from ROM. It handles all the interfaces to the front panel, including the outputs and inputs. Down here, like I mentioned, it actually controls the DSP itself in terms of switching the different algorithms you have. So off the CPU, you have your typical 80s 8 16-bit micro or architecture for the system here. So you've got IC151, which is your ROM. That is the ROM that was on the main board, which we'll talk about. That holds the operating system and your algorithms. IC152 is your RAM. That holds your presets. So when you make adjustments, you save it, they go here. This is backed up to that 3-volt lithium battery, which lives here. So that circuitry is tied directly to that RAM. This is a DRAM, I believe. I don't believe it's SRAM, I believe it's DRAM. I can check on that, I might be wrong. So next on there, so you've got multiple buses here, which something really nice about the schematic that I've noticed is that they actually label their buses with the address ranges that is used for the various things. So the data bus, for example, for the ROM, it's 8000 through FFFF. The RAM is 4000 through 5FFF. The data going to the front panel here is 6000 through 7FFF. So it's kind of neat that they give you the addresses that are being used. A little bit of insight into this unit, the way it works. You've got some glue logic here, which is actually controlling the, these are decoders, probably 74138s, that are controlling the actual address selection for the various devices on the buses. Off the CPU on this side, if it's on camera, yep, it is. So this is your MIDI input, or remote input here, your MIDI input's up here. That's actually being fed directly in the processor as well. So the CPU is handling MIDI basically natively, which is kind of neat. So, DSP. This is your main DSP integrated circuit down at the bottom. So this is a Yamaha part number. There's not a lot of information out there about it. Yamaha used it both in a lot of their professional audio gear, along with some consumer gear too. Some DSP-based surround sound processors, things like that. So it's pretty common IC that they use for quite some time. Now tied to this is IC127, which is your modulation generator. So this DSP doesn't have any way to actually generate any type of internal modulation. You need that modulation for things like your rotary speaker simulation, etc. Different types of effects that require that. Basically a low frequency oscillator. So that modulation data is coming from this IC127, which ties directly to the IC120, your master DSP. So these two chips are basically designed to work together. So getting the data into and out of the DSP happens across these serial buses. So there is your address and data lines coming into this IC149, and then you've actually got the transmit data, which comes off of here, which feeds into the DSP. So all of your audio data is coming across this, along with any control data that's actually making adjustments to the DSP in terms of switching algorithms as well. So what's interesting now is that there is the basically serial data out from the DSP here into the modulation generator. And then the serial data out comes out of the modulation generator back onto the RX data pin of this serial to parallel converter. So your serial data is actually traversing through both these chips this direction, always. And that's how it communicates back to the master CPU. Showing how, again, that basically designed both of these to work together. Off the DSP, you have your RAM. This is critical for the actual algorithms to work in terms of the DSP processing. So with this, you've got 6 ICs. Each one is 4 bits, so 24 total bits of data bus basically on there, and then 8 bits of address bus. So these are actually DRAM based on the clocking, because you've got the various CAS and RAS clock signals coming off of this chip up there. So this is DRAM that is working with the DSP. Finally, looking on the lower left right here, you have your timing generator. So all of the circuitry needs various clocks at various frequencies, both in terms of your converters, your digital signal processing, your clock that runs the actual master CPU, etc. So you've got your master actual crystal up here, which is just a 4 megahertz crystal, feeds down into your timing generator and all of your clock generation circuitry here. So based on this, you've got various quadrature decoding going on. You've got other decoding that's generating all of your various clock signals, which you can actually see coming off of this register chip right here. All those clocks are coming out of IC133 and then driving over to various portions of the circuitry to make this whole thing run. So quick overview of the schematic. there. Now we'll actually take a look at the hardware. Now, one interesting thing is it actually has dual PCM54 HPs. So the PCM54s are a classic Burr Brown digital analog converter. They are used both for the digital analog conversion for the stereo out, switching left and right channels between one of them. And then the second one is used with the successive approximation analog digital converter. That's actually what's generating the analog output there to convert from the previous state. So on the digital side, you've got the classic Yamaha YM3804B. This was the DSP that was used in a lot of different effects processors, including the Rev 5 and the Rev 7. It was actually used in some home theater products as well for digital signal processing for different sound fields. Now, this is actually paired to the YM3807. This is the modulation generator. These two chips are designed to work together. The DSP itself can't generate any internal modulation. So for anything, any effects that require modulation, so rotary speakers, tremolos, things like that, you need external modulation to be driving this. So the schematic outlines this pretty clearly how the two work together. Tied to your main DSP is your RAM. In this case, MB81464-12, so most likely 12 megahertz. 64, so I know these are 4-bit. We'll have to look at the specs in the datasheet. Main processor for the entire unit is the Hitachi HD6303RP. This is actually a microcontroller, which tied with the ROM and the RAM over here, which we'll talk about, drives everything on the unit. It is used to load the algorithms into the DSP. It handles all the front panel interactions in terms of, foot switches, button pushes, things like that. It handles the MIDI communication as well, and then it drives both the LCD and numeric display. So the ROM is a Toshiba TMM24256AP. This is a one-time programmable ROM, 256 words. So earlier devices, this was actually an EEPROM, and you can actually still put an EEPROM in here. They're pin compatible. Later versions, probably cost savings, they went to the one-time programmable ROMs instead of the UV erasable EEPROMs. And then you've got your RAM, which ties to this as well. This is a TC5565PL. This is an SRAM. This is where your user settings and presets are saved when you want to modify your different algorithms. And this is battery backed up from that 3-volt lithium that we replaced earlier. Looking at date codes, we have 14th week 87, 10th week 87. These are, the actual Burr Brown converters are 21st week 87. So 87 is a pretty accurate build date for this, possibly early 88. So it gives you at least the era that this was actually assembled at. So 30 years old. It's definitely getting up there in age. The rest of the TTL logic, at least primarily TTL logic in here, is all 7400 series. Various HCs, I think there's an S in there too. But this is basically all your glue logic that's handling your clock decoding. It's handling your front panel decoding, both for the matrix key scanning coming in and your Charlie plexing going out, driving the numeric LED displays. It's handling your display, the LCD driving as well. It's handling the communication, some serial communication. You've got some parallel parallel decoders in here, because these are actually serial data driven from the parallel data off of the actual DACs themselves. You'll also notice that there is a definite separation from the analog to digital sides. The ground plane is split pretty much all the way across the board right here, just for noise purposes. In audio design, when you have a lot of noisy TTL digital logic going on, you see this a lot to separate, to make sure that digital noise isn't getting into the analog pathways. Here are your two 15-volt regulators, positive and negative, for the analog digital converters and many of your op amps on the analog side. They are mounted directly to the board here, which you typically see often in these older designs. They don't run hot. I had this on for a while and I felt them, so they stay pretty cool. So again, not much concern for the caps in that area. This chip here, which is the IR9311, made by Sharp, this is your comparator that's actually doing the successive approximation analog to digital conversion. Almost all the chips in this board are Yamaha branded as well. So you've got Yamaha making their own DSP engine. You've got a lot of Toshiba branded chips in here. You've got Japan Radio Corp. You've got the Mitsubishi branded chips as well, quite a few of those. You've got Hitachi with the microprocessors. And aside from that, you've got the Fairchild branded DRAM and then the Burr Brown classic DACs. So I hope you found this video interesting. The Yamaha SPX90 and 90 Series 2 is a classic effects processor. Not the greatest by today's standards, but still very useful depending on the application that you're looking to use it for. So you can get these extremely cheaply, especially broken. They're almost always repairable. Power supply is the major cause, as we talked about in here. Very little typically goes wrong with the main board, including the DSP, unless it's been physically damaged by someone. So they are very well worth picking up. I fix and repair primarily vintage synthesizers and effects processors, so please subscribe, and I will have more videos coming soon. Thanks for watching.